revolution that we speak about materials, because every industrial revolution has been driven by materials innovation. Today, our Pope, let's say, presented his new message about artificial intelligence and how artificial intelligence can, let's say, affect and influence our lives, and how artificial intelligence can also affect the new industrial revolution. But it's also important to speak about materials, because today materials are no longer passive components, because they can actually determine performance, manufacturability, sustainability, and supply chain resilience. So every century basically has had, let's say, its proper innovation. So we started with steel, then we moved to polymers, semiconductors, and now we are in the era of nanocomposites that can be merged together with the field of intelligent, sustainable manufacturing. And this is something that I want to present to you based on my research perspective, because I define myself a materials engineer that is able to connect multi-scale science with industrial translation. So smart materials now today require a very smart integration across different disciplines. So as you can see here, these are basically most of my interests that cover material science, additive manufacturing, multi-scale modeling, and fabrication. You see that, at least from my perspective, the need of the correct supply chain, let's say, pass across different disciplines. But why nanocomposites are so important and they matter for industry? So first of all, let's try to focus about the importance of nanocomposite and what they are. So nanocomposites are basically a matrix, a material that is a matrix that collects into let's say, its body, a nanofiller. A nanofiller basically is something that will reinforce and transform the basic properties of the matrix in order to create, let's say, let's call it a super material, in order to improve specific properties, as you can see here in this panel here. We have, with increasing or with the increase of the filler contact, let's say, improved properties in terms of mechanical properties. It can be thermal properties, but magnetic properties, and so on. And why are so important? Because with composites, and specifically nanocomposites, we can get, let's say, something that, let's say, basic materials cannot achieve by themselves. In particular, multifunctionality. They can achieve basically the same target properties, let's say, with being much lighter. They can be easily processable, so we can create different shapes, especially with employment of 3D printing or additive manufacturing in general. And they can, of course, also target a specific durability in terms of mechanical stability, performance, and resistance in general. From lab to supply chain, because we are not focusing in this presentation, at least, only on the specific properties of the material, but how material nanocomposites in particular can, let's say, cover the entire process from the fundamental science towards the end of life of this kind of material, creating a sort of circularity, let's say, from the basic science towards the industrial application. And so, as you can see here in this flow, we go from fundamental science. So because we have to, let's say, deal with the basic properties of the single components, the matrix and the filler, in order to create a good formulation in terms of what? In terms of, let's say, in order to get specific properties that are targeted through the process, the fabrication, but towards a specific industrial application. Because we are not focusing only, we are not just relying on the fundamental science to publish papers. Okay, we at the university were always focused on published papers because this is, let's say, our main output. But it's pretty important to design, to create innovation in order to have, let's say, an impact in the industrial fields. And here comes, let's say, the first case study. Okay, this is something that I've dealt with a lot, also during my PhD. That is the case of biomedical nanocomposites. If we think about our tissues, in particular bone is a nanocomposite because it's made of a matrix that is collagen and is reinforced with a mineral component. And today, based on the need of patients due to traumas, pathologies, so on, we have an increased demand of bone substitutions. And so here comes the idea of fabricating something that goes from the design of specific materials towards something that is actually usable in the medical field. And we speak about medical devices, as you can see here in the last panel here. As you can see here, for example, the integration of prostheses, for example, with bone, or the employment of specific tools to treat, for example, strokes or the other traumas or pathologies. And here, the possibility of using biomedical nanocomposites, let's say here this nanocomposite really can make the difference, because they can be enablers of new possibilities in terms of shapes, in terms of properties that can save time, money, and pain to the patients. Just to give you, let's say, a real application, and something that I've dealt with a lot, is something that is specific for recovering hearing traumas and hearing problems. We know that worldwide, for example, we have a lot of people, millions of people, that suffer hearing loss. And here comes the problem of recovering the hearing capability of the people, in terms, for example, of recovering after traumas of the middle ear. The middle ear is this moving structure that I put in this panel that is moving, that is composed of a thin membrane connected to 3 small ossicles. Just for having a comparison, you can see one American cent, just to show you how small these structures are. And here comes the problem. What if we have, let's say, this membrane that is torn apart, and it's very easy to tear this membrane. Even when we are cleaning our ears, it's very easy to tear this membrane. Or we have to, let's say, change the structure of the ossicles because of traumas. Here's the example and the application of nanocomposites. In this case, a membrane that is composed of a basic polymer, a very well-known and widely spread polymer, for example, polycaprolactone, PLA, and so on, with the addition of graphene. With the addition of small nanoparticles of graphene. Graphene is a very well-known material, especially in the last years, because it has a lot of properties in terms of, for example, improving strength and changing, of course, also the acoustic. In this case, we want to see, let's say, the variation of the acoustic properties of the membranes. And as I was saying at first, I'm trying with my work, I'm trying to connect not only experiments, but also simulations. Because, of course, especially when we have to deal with the biomedical applications, and it's very difficult to go directly to the patient, yes, of course, we need a simulation to predict the behavior of our tools in order to create something that at the very end of the supply chain can be very useful. And here comes, for example, you see these very colorful plots. You see, for example, here the top plot, the behavior of the native ear drum. You see, besides the numbers, you see, let's say, the shape and the colors, and you see that there are materials that can, let's say, replicate quite well what is originally in the native tissue and something that is not behaving well. Okay, these are tools that we can use beforehand in order to provide at the very end of our chain, let's say, the best device with optimal performances. And here comes the industrial angle, for example, of this specific application, because for example, we fabricate this kind of membranes with techniques that can be scalable. In this case, it's electrospinning. And electrospinning is a technique with which we can create nanofibers. We can create nanofibers exploiting polymer solutions and electric fields. And we can create, as you can see also in the pictures, structures and membranes with specific porosities. We can play with our processes, not only with the mechanical properties, but also topological properties. The industrial angle, it can also has a particular interest, of course, also for multifunctionality, as I was saying beforehand, because of course we can engineer our structures. We are not just relying on the simple manufacturing process, but we can also play with the geometries and play with the physical properties in order to create, for example, other specific properties that can be, for example, anti-inflammatory or antimicrobial properties. And all of these applications, of course, have a very good, a very important, relevant industrial value, because we can create something that is not with which we can obtain, let's say, something that is multifunctional, that is light, and is sustainable, because we can create patient-specific devices that are not produced, let's say, full scale in industries, but can be used specifically for the patient. So we don't have waste, and we can get, let's say, a circular ready process for our application. Another example, always in the biomedical field, is to, if we want, as I was saying, to replicate or, let's say, change, substitute the ossicles, the three ossicles that are connecting the membrane with the internal ear. In this case, we can use processes that go from the definition of the material, and as I was saying, the definition of the specific properties of the nanocomposite. We are speaking about bone, so we have collagen and hydroxyapatite, and understanding from the atomistic scale the properties of such material in order to create a new substitute that can behave like the bone or even better. We don't have to, let's say, be bonded to the idea that we have to replicate exactly nature. Nature is a very good inspiration, but let's say through the engineering processes and our competencies, we can also create something that works even better. Works even better from the definition of the material towards the medical device, the final medical device. So we can transform something that nature created with specific shapes in something, as you can see here, the biomedical device, in something that behaves at the same time, let's say behaves similarly, but let's say with the simplification of the geometry. And here comes at the very end of our supply chain, the fabrication properties in order to get, let's say, this device with little material, small cost, little costs, and effective properties. Simulations are at the very core of designing new materials and medical devices. You see here, just in this panel, general panel, simulations that consider the material from the, let's say, the bone, of course, the bone tissue, from the, let's say, molecular structure, and see how different components, collagen, hydroxyapatite, water, let's say, they can play, let's say their roles in making the tissue working. And other simulation, for example, optimization simulations that are performed at the, let's say, at the macro scale, using, for example, finite element models, in order to get the best solution, let's say, that is compatible with the industrial constraints. Fabrication is really important. It's really important because we can design whatever we want, but if we want to pass from material to the device, it's very important to get something that is working, and that is, let's say, that targets our needs. And here you see the fabrication of the prosthesis compared to the American Cent. Here are some images that are really nice because you see, for example, the path of the 3D printer of the prosthesis, and also the application of the prosthesis in an actual human bone, in actual human hair, in order to test together with clinicians if these kind of devices can work also in a real environment. Of course, this is still lab, is not the hospital and real patients, but at least we can test also the ability of the surgeons to deal with new medical devices. Speaking about sustainability, what if we change, for example, the employment of human collagen with other types of collagen, for example, from animals? due to the increased need of bond substitutes, there's an increased need of collagen. I can assure you that collagen, human collagen, is very costly. So an idea could be to use, for example, bovine or marine collagens from waste. Always in the, let's say, with the idea of creating a circular supply chain that is not wasting money or materials towards the industrial application. And here is something that we did actually. We did, and we created through using simulations and additive manufacturing actual substitutes for bone regeneration, as you can see here. And we can play also not only with the materials, but also with the process in order to get what, for example, in order to create materials that during the cross-linking, so let's call it even, let's say roughly the solidification, let's say this, even though it's not very completely correct, we won't get, for example, distortions. If we're speaking about, for example, little bone substitutes, it's really important to create something that is really precise and accurate without the distortions, because otherwise let's say the functionality will be affected. This is something that we can study also beforehand in the lab through simulations and specific experiments. The other application that I want to speak about is play with stimuli. So composite that can rely not only in the specific properties, let's say atomistic properties of the material, but also nanocomposite that can also exploit stimuli. Bone, for example, is a piezoelectric material. What does it mean? It means that bone, whenever it's stressed, it can also release small electric currents that are those that also promote regeneration of the tissue. And what can we do with this? Well, what we can do? Well, we can create, for example, nanocomposite that can exploit this kind of biosignals in order to create substitutes that can perform like bone, or even better, in order to make faster the regeneration of the tissue. Of course, this kind of study requires not only the fabrication of the nanocomposite starting from the scratch, so using, for example, as a matrix, the specific polymer that is piezoelectric itself, and the reinforcement that is a ceramic that improves, of course, the piezoelectric properties. But even though as you can see here in this plot, and you see this parameter that is very, very high, you see 40, 60, compared to bone that is very little, at 1, 2, so we can create something that works even better than bone. Of course, we have also, let's call it side effects, because in using composites or using a filler, of course, we have a side effect, for example, of improving the stiffness. So the ability of the material to be rigid in the elastic regime. Of course, towards the final application and the final industrial device, of course, we can exploit again additive manufacturing. In this case, the classic 3D printing, in order to create a shape that starts from the simulation towards the actual model. Of course, there will be differences, but differences that can be studied, predicted, and even exploited for our benefit. At the very end of this presentation, let's try to find some take-home messages. So let's try to, let's say, put everything together. And in this case, looking at this slide, manufacturing supply chain integration. Of course, manufacturing is a key phase in the supply chain, because of course it's able to improve the supply chain in terms of customization of the products, in terms of distribution of the manufacturing sites, and the possibility to create something that is personalized and that can be created even on demand. So reducing, for example, the logistic burden and the associated costs. Creating, so in terms of supply chain, a very fast response to the need of the final stakeholders, and lowering the total costs. at the very end, nanocomposites, let's say, have a specific and a really important role in the supply chains of materials in this new era, okay? Because we can create something that is really circular in terms of applicability, in terms of recyclability, and the reusability of the materials themselves, lowering the costs and creating something that is specific for the demands of the stakeholders. The future materials must be like nanocomposite, but now in the era of artificial intelligence, we can have let's say now another tool in order to create a high performance, manufacturable, and sustainable, let's say, material and innovation. Key takeaways: nanocomposites are transforming product performance. Additive manufacturing is reshaping supply chains in industry. And sustainability is not anymore something that is put aside as just in the final evaluation, but it's something that is central in all phases of the design of materials in order to get the best device, the best application for our needs. Thank you very much for your attention.
Thank you. Thank you very much, Dr. Milazzo. It's a fascinating look at how material science will directly impact on supply chains. Now, let's move on the questions. On the first questions, what do you consider to be the main challenge in implementing nanocomposites in industrial supply chains in development countries as Peru?
So in my opinion, it's a matter of investments. It's a matter of investments. It's a matter of investments in terms of competencies and equipment, mainly. Okay, because let's say nanocomposites now have been in the field of material science for quite a while. So the idea is to train new generations, let's say, with the idea that they cannot, that they don't have to use just, let's say, traditional materials, but they can play with the design palette in a smart way, also with the help of artificial intelligence. I'm not against artificial intelligence, even though everyone has to use artificial intelligence, let's say, with critical thinking. But let's say the design palette is really open. And so it's a matter of training and investments in order to have the best equipment to manufacture and create, let's say, the supply chain towards, let's say, applications and devices.
Okay. Thank you.
Yeah, greetings, Mario. I was just wanted to comment also that, as you mentioned, the importance of the application of nanocomposites and nanomaterial manufacturing techniques in general is that such methods provide you the ability to control the resulting structure in ways traditional methods cannot. And that's the reason you are able to come up with new properties of already known base materials. And also, there were other questions related to the last one that was asking more about that. If you already identify the application of, for example, carbon nanotubes or graphene can benefit your application, what would be a general cost estimation of changing your regular production change, including these nanomaterials? I know it's a bit of a hard question to ask without having more information, right, about the cost, but that was right.
Well, it really depends on the field we are targeting. Okay, because there are fields in which, let's say, costs are not a problem. Okay, and there are fields in which costs are a huge problem. Let's say, for example, for the biomedical field, let's say costs, let's say, roughly speaking, are not a problem. So if you are able to get, let's say, the best functional device the best functional device, even with the high cost, since this can change lives, is not a big deal. So the impact will be very high, even though the cost will be very high. There are other applications, for example, the automotive industry, for example, in which, for example, we cannot afford, let's say, the latest advancements of nanocomposites. We cannot afford them because, of course, we want to keep the prices low. Other fields, just to make it just another example, the aerospace field, of course, costs are not a problem. So in fact, most of the advancements that we have seen, let's say in the recent years for composites, are mostly related to the aerospace and military fields. Let's say fields in which costs are not a problem and costs are not problem, so we can get whatever we want. Of course, there's another problem related to materials, let's say neat materials. Let's say if our components, our devices will be made of the so-called rare materials, of course, costs will be very high. And again, is it worth it? So it really depends. Let's say the answer to this question, it really depends on the field we are targeting. However, let's say from the engineering point of view, it's not a big deal. From the engineering point of view, as long as we have money, we can do basically everything. Of course, reality comes in this case, and in industry, of course, requires also a techno-economic analysis that we cannot skip, of course.
Yeah, there was also a question in Italian, so I guess we don't need to translate it. I just send it to you as a direct message.
So it's which is the challenge that is most important for bioengineering and biomedicine. Okay. Also here, it's a trade-off. It's a trade-off because we ideally from the research perspective, we want just to improve the functionality of our devices and create something that can be hosted properly without rejection and so on. But let's say economic accessibility is, let's say, much more important from a social perspective, of course. So we always have to find the best trade-off between the two of them.
Okay. Just give me a second. Álvaro, tú que eres el moderador, tenemos tiempo para más preguntas, pero tenemos en realidad bastantes.
No, vamos por la foto final. Ok. Thank you very much, Dr. Milazzo.
Okay, we're
just
going
a
to
moment,
wrap it up
please.
with
So we can take a photo
a group photo, yes.
to commemorate your participation.